In this lecture we talk about finite fields. So we start with Frobenius Endomorphism. So consider a field F, and this field is of characteristic P. So consider this map from F to F. So this is a homomorphism from F to F, so therefore it is called an endomorphism. And it takes an element x of F and maps it to x to the power of P in F. So then this a plus b to the power of P is AP plus BP, and AB to the power of P is AP times BP. So this you can see immediately from the binomial theorem. So you do the binomial expansion like this, and you will see that the prime P divides P choose I, and therefore all these terms will be 0 because we are working in the field of characteristic P, and therefore you just get AP plus BP. So this is the result here, and AB to the power of P is AP times PP. And now you can see that this varphy is a injective homomorphism because it will only map 0 to 0. If you have a non-zero element, it will map it to non-zero element. Now since the field F is finite, so we are considering finite fields here. So it's a field of characteristic P, and say this field is finite. So if the field is finite and of characteristic P, so we have a finite field and you have an injective map. So since you have injectivity and finiteness, this will imply surjectivity. Because both these fields are finite, you have an injective map, so unique elements gets mapped to unique element. And since the field is finite, you go through all the elements here, you will come with all the elements here. You have an endomorphism, so number of elements here is same as number of elements here, and you're mapping unique elements to unique elements. So you have surjectivity. Now therefore you see that every element of F is a pth power because of this map here. So we have a finite field, characteristic is P, you have this map, that means every element of F is a pth power because of, again, surjectivity of varphy. So this leads us to a definition of a perfect field. A field of characteristic P is called perfect if every element of the field is a pth power. Just like here in this case, every element is a pth power. Again, for this case, it results from the map being surjective, this map x to the power of P being surjective. Now for a field with character is 0, we already know that irreducible polynomial is separable. So this we saw before, that irreducible gives you separability for free, and this was seen in the lecture separable and normal. So separable and normal is a very important lecture, and it is a good idea to recall the results which we discussed in this lecture, because all those results are going to be now used in this lecture. And so this result irreducible implies separable. This followed from the fact that greatest common divisor of this polynomial F and derivative of F is 1 for F irreducible. Since degree of the derivative is always degree of F minus 1. So you can see degree of F is say n, then degree of df would be n minus 1. And this n and n minus 1 are co-prime, and that is what led us to greatest common divisor being equal to 1. But for finite fields, if you have a non-zero polynomial, you could still have the derivative as 0. And that would imply that greatest common divisor of F and the derivative of F is not 1. So you cannot just simply show separability using this result. So for example, say f of x is x to the power of pk, and we saw that for an inseparable polynomial, again in this lecture separable and normal, px is equal to g x to the power of p for something. So for example, what is the derivative of this? The derivative of this is pk times x to the power of pk minus 1, and this derivative in characteristic P, for finite field with characteristic P, this df is just 0. So you cannot have f df equal to 1, you just have a 0 here. So again, all these results here we are just recalling these results from this lecture, separable and normal. So we want to prove an analog of this theorem. Irreducible implies separable. So separability comes for free in characteristic 0, and therefore sometimes we just say that polynomial f is irreducible, and then we automatically mean that its roots are distinct, that it is separable. So now we want to copy this result for finite fields also. So say you have a polynomial px over a finite field. This finite field is also of characteristic p, and this polynomial is irreducible. Then it would imply that this polynomial is separable. So we will use contrapositive, that is, inseparable would imply reducible. So again, recall from the lecture on separable and normal that if a polynomial px is inseparable, then it is of the form gx to the power of p. And say this gx to the power of p will look like this, gxpn. So say your gx is given as this cn xn, just some standard form, cn minus 1 xn minus 1 all the way to c0. So now instead of x, you plug in x to the power of p everywhere here. So xpn xpn minus 1 c0. Now we have seen this, that since we are working in a finite field with characteristic p, every element of f is a pth power. So every element of f is a pth power. So this we are going to use here. So cn is a pth power, so you write it as bn to the power of p. cn minus 1 is a pth power, so bn minus 1 to the power of p. The c1 is a pth power, so b1 to the power of p. c0 is a pth power, so some b0 to the power of p. So now you can use multinomial theorem, raise everything to the power of p. So only these are the elements which will remain. Everything else will become 0 because we have a finite field with characteristic p. So all other terms will become 0, precisely the way all other terms became 0 here. So now you see that p of x was inseparable. That implies that it is reducible. So see, this p of x is inseparable. This was the inseparability condition. This is how was the inseparability condition we showed in the lecture on separable and normal. And now this becomes reducible because you can see it's a product of p same factors. So all these multiplied p times gives you p of x. So now we talk about existence and uniqueness of finite fields. So this polynomial f of x, say, equals to xp to the power of n minus x in a finite field of characteristic p. So we are writing fp as a finite field of characteristic p. So this lies over a finite field of characteristic p. So you see its derivative is, you take its derivative, so pn xpn minus 1. So since you are in characteristic p, this first term will be 0. You have p to the power of n here. So this just becomes minus 1. Now since this derivative is a constant, derivative of this is a constant, so derivative has no roots at all. And this would imply that polynomial has no multiple roots. So this condition, that derivative and the polynomial have to share some roots to have multiple roots, this was proven in the lecture separable and normal. So since derivative has no roots, the polynomial has no multiple roots, and since it has no multiple roots, that means all its roots are occurring only once. So this is a separable polynomial. So we have proven that this polynomial is separable. So this is a separable polynomial, but notice that this is not irreducible. You can take x common. So separability does not imply reducibility. But you see that this polynomial, although reducible, is separable. So since it is separable, it has exactly p to the power of n roots. That is the degree of the polynomial. So you know the number of roots counted with multiplicity is precisely equal to the degree of the polynomials. Since it's separable polynomials, all the roots are distinct. Therefore f has exactly p to the power of n roots. Now the elements of the splitting field comprise precisely of p to the power of n roots of f of x. So say if r1 and r2 are roots of f, then both r1 and r2 will satisfy this equation x pn minus x equals to 0. If you put r here, the root, this will become equal to 0. So if r1 is root, so r1 to the power of pn, so r1 to the power of pn minus r is 0. So this is 0. So this is equal to r1. Similarly r2. You add them raised to the power of pn, you get r1 pn plus r2 pn. Again binomial. You are working in characteristic p. All of the terms would be 0. And this will just be r1 plus r2 from here. You can see the product and the inverse. So you can see that these roots by themselves, so roots of our polynomial f here, they themselves form a field. So within the roots you have a field. So roots by themselves form a field. So roots of f themselves form a field because they are closed under addition, subtraction, taking inverses and so on. So roots of our polynomial f, they form a field. So we have constructed the field just by considering the roots of this polynomial. So we set the splitting field as f p to the power of n because it has p to the power of n elements, p to the power of n roots which are forming this field. And the degree of extension is fpn over fp is precisely n. So notice that this is n here. The polynomial has degree p to the power of n, but this is n. And to see this, you can see this. So look at the direct sum of these fields fp. So take n of them. So this is the dimension, n of them. So fpn over fp, this is n because the first place you can fill in p ways, this you can fill in p ways, this you can fill in p ways. So total number of elements is p to the power of n. So fp is a finite field of characteristic p. So it has precisely p elements. fp has precisely p elements. So you can see the dimension is n and the total number of elements p to the power of n. So we have proven the existence, and now we prove the uniqueness, and uniqueness just follows from the uniqueness of splitting fields. So for uniqueness, you note that the field of dimension n over this finite field, you're taking direct sum, has p to the power of n elements. So from every field you can fill the first place in p ways, second place in p ways, last place in p ways. So total number of ways is p to the power of n. So if you just skip the 0, then the multiplicative group is of order p to the power of n minus 1. So this implies r raised to the power of p n minus 1 is equal to 1 for r in the multiplicative group. So the star here denotes the multiplicative group. So that is fpn star is just fpn minus 0. 0 is not there. So since this holds, that means r is the root of the polynomial this xpn minus x. So if you put r in here, you will get rpn is equal to r, and therefore this statement would hold immediately. So this would immediately imply this. So therefore this f pn, this is a splitting field of our f, which is this polynomial, and this splitting field has p to the power of n elements. So fpn is a splitting field for f, and the splitting fields are unique up to isomorphism. So we have shown the existence and uniqueness of finite fields. So after this, we want to come to Galois correspondence of finite fields.